this is the first element of these three last elements we will see. Okay, we will see generic trees today. Next class we will see graphs to create some path. And the last element is state problems. It's like a way to resolve games. Okay, this is the last three things we are going to see. Okay, last three concepts. Okay, I think this is a very, very good number of concepts related to Prolog, to have a good understanding about this subject. Generic tree. Okay, so this is another generic trees are like similar to binary trees. It's one of the most important data structure to organize information in computer science. And here the difference is we can have many, not only two, we can have many, for example 1, 2, 3, 4 or 5, or not 5, 2. We can have many songs of one tree. Okay, and for that the same here we can have another 3, for example, something like that. 6, 7, 8. Okay, now each node can have any number of songs, not only 2 as we see last day in binary trees. Now trees will have many songs. Okay, how we can represent that type of trees? We will have a list of songs. It's nothing like, let's go to 3, 1. Sorry, 3, 1 will be something like T, and now this label, and then a list of trees. Okay, inside this list, here we have 4, 1, 2, 3, and 4, and the first one will have the label 2 and 3 more trees. Okay, this is the number 2. Here we'll have number 6 and an empty list that represent this node have no more songs. And the same with this 3, 7, and no more songs here. Okay, and here we have 8 and no more songs, and for here we have 3, 4, 5, 3 and no more, and 4 and no more, and 5 and no more songs. Okay, do you understand the representation for these three? So we have an element T, the label, and a list of songs. Okay, any question about that?
No.
Okay, I'm gonna represent another more simple tree, because let's go to tree 2. Let's go to represent another more simple trees like 1, 2, and 3. 3 and 4 is 3. Let's go to represent this 3. It's like T label, the first label is 1, and a list of trees. The list have 3 trees. 1, 2, and 3. The first one is this one. 2 and no more, empty list. 3 an empty list of songs, and 4 an empty list. Okay, this is the representation for these 3. Here we have the 2 examples, this one and this one. Okay, nice. Let's go to find elements inside a generic tree. Let's go to find to search. Or let's go to create a predicate to say if one element is inside some member, the element in a generic tree. It's like this is, we need that and we need that. We have no more arguments because the result is when the element exists in a tree, that will be true. It is true if element E is inside, is a member of generic tree. Okay, this is our next predicate. Let's go to create a member of one element in a tree. Here, in the case of generic tree, we have a main differences. We have a main difference between the binary trees, because in binary trees, nil or was a valid tree. But now in generic tree we don't have something similar. We don't have a null or a nil tree. The first or most leader tree for us will be a tree with only one element, something like tree of one element, whatever, and an empty list. This is our most little tree in generic trees. We don't have nil here. we have this only one node tree. And here you can see we have two type of structure. We have we have a T, something like T and whatever inside, and we have a list. We have two elements, a tree and a list. So we have to deal with two different data types. We have trees, and inside this tree we have list. Okay, so we have to deal with two different type of data types, trees and lists, in the same structure. So the trick here is to create a predicate for list and a predicate for the tree. Okay, well, to divide the solution of this problem, creating like two separate predicates to resolve that. Okay, we have one predicate for list, is one predicate for the tree, for the tree, and one predicate for the list. Okay, let's go to separate the resolution of this problem, creating two parts of two predicates, two different predicates, one for trees and one for the list. Okay, let's go, for example, to create here the predicate for the tree. So member of one element in a tree with what is the most simple case to find one element in a generic tree? Is very similar to the binary tree. What is the most simple case I can find?
Like the first one in the root, or
sorry?
Like the first one in the root on the top.
Yeah, if the element is the label of the top of the, something like that. If the element is the label of the top of the tree, it's like if I trying to find the number one, and the number one is here, is in the top of the tree, I finish. Okay, I get the solution. That is true. The element is in the label of the top of the tree. Okay, everyone agree with that?
Yes.
Yes. Okay. The second part is, okay, I have the option to find here, or I have the option to find the element, the tree. I can say here label if you want, and here this is the list. This is the list of tree list. Okay, this is a list of trees. And what if the element if is not unified, sorry, not unified with the label, that will be true if is member the element in the tree list. So if that is true, if the element is not in the label, the top of the tree, and the element is in the tree list, the element is a member of the tree. Okay, remember the logic rule. If that is true, if all that is true, then that will be true. So now we have here a predicate for list of trees, because that is a list. So now we have to create the predicate for the list. So remember, is done. That is as we did before. What happened with the empty list? I have to write I have to write a solution for the empty list or not? What do you think? In this case, what do you think? Do you think we have to create a line for empty list or not?
I don't think so.
Why, Michael? Why you don't think so? We don't need a line for empty list here.
Because didn't we include it with the first one, with the with the element in the root?
Something like that.
Like in line 47.
47. This is the line 47 is a line for a tree element when the element is in the top of the tree, but here that's if a tree, not a list. This is a tree. T and parentheses. And now we have to create a predicate for the list of trees, because here we have two structures at the same time. We have the structure of the tree, and inside we have a list of trees. Okay.
Okay, yeah.
So what happened? This is like we finished here. We finished here with the part of predicate for trees, because usually we will do the same. Do something for the first level. Do something for that, and here make the relationship between the tree. This is a tree, generic tree, and the list of trees. This is the list of trees. You have to see the difference, because that is a list. To list tree. To change the name, because to reinforce the idea of that is a list of trees. Okay? This is a list of trees. So we have a list of trees. Okay? This is very important to make the difference here. We have first we have a tree, and then a list of trees. So this is a list. We have to deal with that as we usually do with list, with an empty case or an empty list case, and separate first head and tail. But what happened in this case with the empty list? That is false. That is false. That is false. Why that is false? Because if this is an empty list of trees, it's impossible the element is here inside. So that is false. And when something is false, we didn't write. So we don't need in this case to write this option, because that is false. And when we want to represent that something is false, we didn't write in Prolog. Okay? So this is a comment. This line is not inside the code. Okay? What did you prefer? Something like that. Okay? It's okay or not? What happened?
It's a,
It's okay.
It's okay? Okay, let's go to continue. This is the first time we create a predicate for generic trees, and at the beginning will be a little bit difficult, but
sorry, one question to
Yeah.
line 49.
yeah,
We excluded when the element is not in the label.
yeah, because we want one case is the element is in the
Yeah.
it's in the level of the top the tree. If not, we have the other case. This is the case when the element is here, and this is the case when the element is not in this.
Okay.
And now, when the element is not in the top, we have to check if the
Okay.
element is
Yeah.
in the list of trees.
Yeah, sure. Okay, yeah, the label is the root. Sorry, I was a bit confused.
Okay?
No, it's okay. Thank you.
Okay? Okay. Res, any question? Don't hesitate. If you need to make some question, please do. Don't. I know it's something is sometimes difficult to make questions in this situation, but please don't worry about that. If you think there's some stupid question, don't worry. Please do your questions. Okay?
Yes.
Okay. Gabriela. Gabriela. Can you hear me?
Yes.
Yes. Are you understanding that or not?
Yes. Yes.
Okay, nice, perfect. Agnes,
Yes.
Colleen.
Yes.
Okay, nice. Colleen, did you see that before? Generic trees, or never see that this type of structures?
Not
It's the
quickly, but
It's the first time. It's your first time. Sorry, Colleen. I can hear you. Can you repeat?
sorry. I've seen it really quickly, but not
Okay.
that much.
Perfect. Mario. Hi, Mario.
Yeah.
Is the first time you see this type of data type of generic trees or not?
Well, yes.
Yes. Okay. Okay. Please, if you have any question, please don't worry. Ask whatever you need. Okay.
Yeah.
Okay.
Okay. Let's go to continue. So we don't need this line because that is false. If the list of trees is empty, the element is not here because there are nothing here. Okay. And now let's go to apply the same trick we do always with list. It's like head and tail. And it's very important to understand what we have here. Please tell me what's that? The head, in this case, what's that? This head. What's that? Please tell me. What we have here. Try to describe that.
It's the root of a subtree.
No, this is what? This is what?
The first element.
No, but it's the first element of a list of trees. So what's that? What's that?
Label.
Sorry?
Label.
I didn't understand. Can you repeat?
Label. No.
A label? No, it's not. It's not only a label. It's something more. Something more. What's that? What's that? What do we have here in the? What is the head of a list of trees? This is a list of trees. So what we have here?
The first tree.
Yeah. The head is a head tree. It's a tree. Okay, this is a tree. That is here is something like T, a label, and a list at I don't know what are inside, but it's something like that. Inside the head tree, we have something like that. It's a tree with a label and a list of trees that will be empty or will have a million of trees. I don't know what we have inside this list of trees. Okay, but this I know that is a tree. Okay.
Mm-hmm.
And what's that?
The other tree.
Yeah, it's a list, and the other part is the head. This is the head. Head is something like that, and the tail is a list of trees. It's a list of trees. Will be empty. That will be empty, or will be a tree with a label, and inside more elements, whatever, and probably another tree, I don't know, with a label and another tree, and so on. I don't know how many trees are here, but that will be or empty list or a list of trees. Okay? So, if we want to check if this element is inside this structure, what I have to do? What I have to do to check if the element is inside this structure, this list of trees? I have to check if it's here or it's here. No? I have to check if the element is in the head or is in the tail of trees. Okay? So how we can check if the element is in the head? It's like, remember, element in the head. Okay? The first option. The element will be in the head. It's something similar to this one. Or element is in the first node, or and if not, where? If not, if element is varamass, if not, this is is something similar to not. Not is equal. Okay. So if it's not here, where? Remember, element in the tail of trees. So the element, I can find the element here in the tree, or I can find the element in the tail. Or if you prefer, it would be better to do that. Or it will be better to do that, more simple. Or is here, or if not, you can find here or here. will be more simple to, okay, doesn't matter what I have here, if true, if it's in the tail of trees, here or here. And that's all. Any question?
No.
To write. Okay, let's go to check if that works. Okay, let's go to check. I'm sorry. Okay, sorry. Okay, let's go to check if that works. Let's go to open Prolog. File consult. The generic trees. Okay, I have one error here. Let's go to check. Warning, line 54. Here. Okay, I'm not using this variable because I'm only checking the head, so I have to write that. It's better. If I'm not going to use this tail. I have to write this anonymous variable is like underscore. Okay. Now I'm gonna share this file with you if you want to check by yourself. It's the generic tree. Okay, if you want to check or continue writing this file, the next examples or next exercises, you can do there. Okay, let's go to check if that works. Make. Okay, now there are no errors and no warnings. So now let's go to check, for example, with this 3, 3, 1. Let's go to check with this 3. We have 3, 1 and 3, 2. This is a little bit more. This have 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's go to check if 3, 1, the 3, and number 1 in 3. 3, 1. What happened here? Okay, I probably have an error. Okay, because this is a comment. I have to close this comment. Okay, I have to close this comment here and open here. If you want to check, you have to do the same. Close here. And open here. Okay. I think now she's okay. Okay. Make listing 3, 1. Okay, this is a 3, 3, 1. And now, okay, Prolog say, okay, yes, that is true when the 3 is this 3, is 3, 1. I'm gonna share this file, this new file, with the modifications. Okay. Can find is check if the number 8 is inside. And Prolog say yes, no problem. Let's find any element inside the tree. We can check the time. Prolog need to find that. Okay, 14 inferences to find this element inside this generic tree. Did you check by yourself?
Yes, it's working.
Okay, nice. Next predicate. Next predicate. Any question for that or not? Let's go to find a list of leaf in a generic tree. This is when we need a tree and a list of leaves. Okay. Now we need that to input, and this is output. Okay, that is true. It is true if list of sorry, it's not sorry. Is if list of leaves unify with the list of labels in tree leaves. Okay, do you understand that? So the idea is if I have this tree, for example, if I have this tree, the result have to be list 2, 3, and 4. Okay. Do you understand what is the purpose of this predicate? Yes or no?
Yes.
Okay, nice. So, how let's go? We're going to create leaves. That, remember, we will have a predicate for trees and a predicate for list of trees. Okay, so we have to check, for example, what is the most simple case I can find. Try to think about what is the most simple case, and I'm gonna leave you around 5 minutes to think about that and reconnect it then. Okay, try to think what is the most simple case here. Try to think what is the most simple case, and then try to create this predicate for trees. And then what happens if you have a list of trees? Okay, try to create these parts.
Can you send the rest of the text? The whole text?
I can send. Okay, I'm gonna send you that. Okay.
Thanks.
Okay, we will reconnect in 5 minutes. Okay, and tell me what do you have? 5 or
Okay.
a little bit more. Okay, try to think about. Try to do whatever. Try to write something. I know it's difficult for you now at this moment, but try to write whatever. Okay. Okay. See you in some minutes. How's it going?
Yeah.
More or less.
I didn't try it yet. I'm in still trying some things, but
Can you share your screen?
I can.
Okay, nice.
Yeah, it's not so much. I don't know. I tried some things, but
Okay, let's go to see the first part, line 73. 73 is 73 is not true, because remember we have a tree, and the second argument here is a list.
yeah, of course.
So what is the most simple case? We can find, if we want to find a list of leaves, what is the most simple case?
One leaf.
Yeah, and what is a leaf? This definition is a definition for a leaf is it's a tree without songs.
Mm-hmm.
So what we have to put here in, after first comma? What? Yes. What you?
Like,
How you represent a tree without songs?
no.
This is a list. Here, the generic tree, you have a label and a list of trees. What happened if you? So this is a list.
Mm-hmm.
And how you check if you have a leaf?
Wait. Sorry, I didn't get it.
If what happened if you write there an empty list?
Here.
Yeah, it's like, okay, I have a tree with a label and no songs. This is a leaf.
Okay, yeah.
This is a leaf in this representation.
Yeah, sure. Yeah.
This is a leaf. And if you have a leaf, what you had to put here? Inside that.
Only.
Yeah.
This one.
Yeah. This is the solution. This is the solution for if you have a leaf.
Mm-hmm.
If you have a leaf, the solution is a list only with the label of this leaf.
Okay. Yeah.
Okay? Yes or not? What about the rest of the people? What do you think about that? Do you agree or not? Hi, Camille.
Okay.
What do you
Yes,
think?
you agree.
Yeah? Gabriela?
I don't understand the predicate.
I'm sorry.
What?
Sorry, Gabriela. The sound is very, very, very bad. Can you repeat, please?
I think I don't understand the predicate.
You don't understand what we are trying to do, or what? What is your question?
Yes.
You don't understand what we are going to do. Okay. The idea of this predicate is create a list with all the leaves of a tree. Michael, can you show one example of the tree? Here, for example, yeah, here. In line 22 to 24, we have a tree with this structure. Have a leaf. I'm sorry if I don't define what is a leaf. A leaf is one element or a node without songs. So it's the last part of a tree, the last element. In this example, the tree from line 22 to 24, we have 3 leaves. It's 2, 3, 4. Can you tell me what are the leaves in the example of a tree from 11 to 16? Can you tell me what are the leaves here?
7.
Sorry?
6, 7, and 8. 3, 4, and 5.
Okay, nice. Okay, that's his idea. The idea is here is 3, 4, 5 because that have no more songs. 3, 4, 5, and 6, 7, 8. Okay?
Yeah, okay.
This is the idea. We want to obtain a list with all of the leaves in a tree. Okay? Okay. Nice. And they were trying to resolve. Please, Michael, if you can.
Yep.
Download. Okay, nice. In the first part of the solution, the most simple case for us is what happened with a tree with only one element. I remember you, in this case, the most simple case is a tree with only one element.
Yes. Now I understand.
Okay, we don't have a case as we have in binary trees, something like a null or nil tree, an empty tree. Mostly the tree for us in genetic trees are this one. It's a tree with it's line 73. It's a tree with only one element. Okay, and this is the solution when we have only one element, one node. We have this is the result, the list with this label. Okay, nice, perfect. Now we are trying to resolve line 81. Remember, you write there, and I write this comment, line 79, to write here after this line the predicate for the list of trees. This is not a list of trees. Probably you have to copy these 2 lines after line 77, because this part is for trees, not for list of trees. So please cut and paste. Okay, nice, perfect. So probably you can delete that line 77. Okay, nice. And here, can you write? Can you put the font of the text a little bit more great? Is it possible? Nice, perfect. Nice. Here we have that's nice. Please delete what you have after the comma, because this is the result.
This one.
Yeah. Delete that, because this is the result. We are going to obtain the result later. And now here, please write a variable like a list of trees, and delete the bracket because it's a variable. We don't need. Okay, perfect. This is a list of trees. Nice. Now we have to check what happens if the list of trees is not empty. So here, here, please write what happens if list of trees are not empty, an empty list. Yeah, perfect. To say is like a slash or equal. The other, yeah, the other slash equal. Not equal, that means it's not equal to empty list. Okay, we have a case of empty list, and what happens when it's not an empty list. Nice. What happened? We have to check leaves for the list of trees. List of trees, exactly. Okay, and now comma, and when that is true, please write there a new variable, for example, error or whatever you want. It's like the result. Nice. Okay, when that is true, what do you have in error? If that is true,
my list of leaves.
Yeah, you have the list of leaves for this list of trees, no? So you have the result. So what do you have to put there? What do you have when that is true? What do you have to put there? If you have no,
only R.
Yeah, it's the same because because if you have the list of trees of leaves, that list of trees, the solution is the same. Please go to the example up of the tree, or the a little bit more up, here. Okay, line 22 to 24. If you have the list of songs of the trees 2, 3, and 4, the list of leaves in the total trees are exactly the same.
Yeah, of course.
Yeah, it's the same. It's the same. The result is the same because this list of these three, the first node is not a leaf, so it's not included in the list of leaves. Okay. So go down again. Nice. Go down again. What happened of the rest of the people? Do you understand or not? Hi.
Yes.
Yes.
Yes, yes.
Okay, nice. So now we are finished the part of. Please copy line 73. Copy line 73. No, after line 75.
Okay. Yeah.
Because this is the part of the predicate for trees. You can delete that, and let's go to create the predicate for. Let's go to create the predicate for list of trees. So perfect. This is now you have list of trees. So let's go to apply the same rule we apply always for list. So we need a case for empty list and separate hair and tail. So empty list. What is the solution? No. First empty list.
Yeah.
What is the solution? If you have an empty list of trees, how many, what is the solution of the list of list?
Empty list of leaves.
Yeah, exactly, yeah. An empty list, because you don't have nothing inside. Okay? Everyone agree with that?
Yes.
Okay. Nice. Second part, please. As always, leaves and head and tail. Nice. And the solution to the end. Nice. Perfect. What is the head? What is the head? What is the head? What do we have in the head?
A list of.
No.
No, it's.
This is a list of trees. This is a list of trees. The first element of a list of trees, what is? What is the first element of a list of numbers, of integers? The first of elements of a list of integers, what's that? It's an integer, no?
Yeah.
What is the first element of a list of trees?
A tree.
Yeah, head is a tree. Yeah, it's not a list. The head is a tree.
Yeah.
Not a list. Okay. So please give me the leaves of the tree head. You just resolved that problem 11 lines 77 to 80. Now you have a way to obtain the list of leaves for trees. Please apply that. So only apply these leaves for the tree. No.
Not here?
No, not here. After, yeah,
Here.
yeah. No, leaves. I want you write the predicate leaves. Leaves and use the head. Okay.
Oh, sorry.
Okay. Perfect. When that is true, write there a variable, wherever, error if you want. Yeah, perfect. Actually, that doesn't matter because the variables, you can write error.
Yeah.
Because
Okay.
it's a different variable. Okay. When that is true, what do you have in error? Because I remember the head is a tree. I don't know, that tree will have 1,000,000 of nodes. I don't know how many elements are inside this tree. Probably will be empty or not empty. It's a tree, but probably will have only one node, or will have 100, 1,000,000. I don't know. So if that is true, if leaves give me the list of leaves for a tree, what do you have in error? Please try to describe what do you have in error.
A list of trees of the head.
No.
Of the leaves of the head tree.
Yeah, it's the list of leaves. List of leaves for the tree head. Okay?
So I actually have this one.
No, please.
No?
Don't write nothing there. Please only put the focus. Only put the focus to understand what do you have in error. Put the focus there. Try to think. Okay, if leaves give me a list of leaves for a tree, what I have in error?
A list of leaves.
Yeah, for this tree. Okay, nice. But now we have to check what happened with the tail.
Mm-hmm.
So write comma here. Yeah, nice. And what happened with the tail?
And then again, leaves and with the tail.
Yeah,
And
exactly.
then you have a list of leaves of the tail.
Yeah. Now
Then you have to append.
we have, because this is a list of trees, and here you can write R2, for example, a new variable. Nice.
Mm-hmm.
What is the solution if that is true? We have the list of leaves for the head and the list of leaves for the tail. What is the solution?
Both lists together
Yeah. How we can put these two lists together?
with append.
Perfect.
I name it. I don't know.
Nice. Perfect. No. Okay, it's perfect.
And then I have here my solution R3.
Yeah, that's all.
Oh, okay.
It's extremely simple because you only have to call to the correct predicates. Don't think about how to resolve. Only, okay, I have the leaves of the head, I have the leaves of the tail. Put everything together. That's all.
Mm-hmm.
And write the case 84, the line 84 for empty list. Is more or less the same we did with list.
Yeah.
We have a case with empty list and a case with head and tail.
Mm-hmm.
And that's all. Please check if that works. If you can.
I have a wait. Some Prolog is syntax error.
If you can share your file and we can try to resolve the. If you want, I can try to check my computer. If we have any error, try to resolve.
I can share it with you, but I think I missed up one comment in line. Here.
No, you have to close. Yeah, you got line 69, 69. You have to change the order. It's asterisk and
yeah.
No.
This one was the problem.
Yeah.
Okay. Now I don't have any errors. So I'm taking this tree 2.
You have 3-1. You can check. You don't need to copy. You don't need to copy. No, you don't need to do that.
No, it was in a comment. Yeah.
You have in the same file, so you only have to.
Yeah.
You only have to.
Like this.
To use it. You have 2 trees now. To generate trees, and you have the solution for both. So you can check. We don't see your Prolog. I don't know why.
Sorry. Wait, I can. I think it's on the wrong window.
Yeah. Okay.
So I'm taking the leaves. Then I'm taking my tree and my result.
Yep. 3, 1.
Okay.
So, I don't know why. Probably
3, 7, 8.
6, 7, 8,
Okay.
3, 4. It's okay, no?
Yeah. I don't have the right 3. I forgot the 4. Sorry. Yeah, it's okay.
It's okay.
Mhm.
Nice. So this is
Thank you.
the solution. This is the solution for. I'm gonna share my screen. Please, Michael, share your file.
Yeah. 1 second.
Share your file, and we will continue with this file.
So
If you want, I can repeat here. I can do here very fast. It's like particular for trees. T. Did you share?
yeah, it should be.
Yeah. Okay, nice. Let's go to the load generic trees.
There's only this one error with the 4 in the 3 with the one number.
There an error?
No, I just forgot the 4. Sorry.
And
In 3, 1.
Okay. Okay, file, open, generic tree 2. Okay. Okay. You forgot the 4 in your definition of the tree.
Yeah. In 3, 1, I forgot the 4.
3, 1. And number 4 is 4 is 6 2
Like here is
3,
the 4 is missing.
yeah. So
Yeah.
it's 3, 4, an empty list.
Yeah, exactly.
Nice.
Thank
So
you.
let's go to check this one file. Let's go to file consult generic tree 2. We have a singleton variable in line 80. Let's go to resolve that too. What happened line 80? 80. Yeah, because we're not using that. We are only checking the list of trees. If not, okay, nice. Make now it's okay. And now this thing list. Sorry, tree 1. Okay, and tree 2. Perfect. So listing leaves. Nice. This is the first part. This is the part of the tree for the most simple tree, and for this line the thing we only do here is call to the leaves for the list of trees. That is very simple. It's only connecting only connecting the leaves and the list of trees. And the second part is for list of trees with an empty case and head and tail. As always, we check the leaves in the head, we check the leaves in the tail, and append everything. Okay, Why we don't need to change? Because I told you that there are different predicates. This is a predicate, and this is another predicate. Why we don't need to change the name? Can you give me an answer for this question? Why we don't need to change the name if are different predicates? Who can tell me why we use the same name if I told you there are different predicates?
Because there are different inputs.
Yeah, because here we have a tree and there are no Prolog can difference these two predicates, because here we have a list and here we have a list. We can change the name. For example, if we change here the name of list of tree and list of tree, and here list of tree, we can change, but it's not necessary to do that. We can see that as different predicates. This is a predicate for trees, and this is a predicate for list of trees, and this is a predicate for list of trees, and this is a predicate for list of trees. Okay, the name is the same. The name is exactly the same, but we have different predicates, because this is a list for tree, and this is a line 84 is a list for list of trees. You can see the difference or not, or is difficult for you?
Now I see it, yeah.
I can change the name if you want, and you can see the result is exactly the same. The truth is there are different predicates. This is one predicate, and this is another predicate. One for trees and one for list of trees. Okay, I'm gonna share that for you. If you want to check by yourself. Okay, nice, perfect. Let's go to do some predicates more for generic tricks. For example, one simple one is like how to count a number of elements in a tree. Count. We have a tree, and we have here a number. It is true if n unify with the number of elements in tree. Please try to resolve that. Remember, always the same for generic trees. A predicate for trees and a predicate for list of trees. Okay? Please try to resolve that by yourself, and we will reconnect in 5 minutes. Okay?
Okay.
I'm gonna send you this file for you with the text. Okay, nice. You have the file. Please try to resolve that. Think about induction and in both cases, okay? See you in 5 minutes. Okay, Gabriela, can you hear me?
Can you hurt me?
Yeah, I'm gonna use your code to resolve, okay? I'm gonna copy your code and try to modify the things to resolve that, okay? Because your sound is not very good. I don't know if your internet connection is good. Okay, I'm gonna copy your code and paste here. Try to, okay. This is your code. For trees. Okay. You have to. This part used for arithmetic of piano, but now we are using numbers, not piano. So that's nice. That is good, but it not in piano. You have to write here what? A number 1.
Wait, we need to share your.
Okay? Here. That's.
I don't see your screen.
Sorry. I'm gonna share. Sorry. Now. Okay, now. Here you have N0 before.
Yes.
Okay, it's okay for piano, but now we are using numbers, usual numbers. So here you have to write number 1. Okay. It's better. Sorry.
I think that the program don't understand the number just with the arithmetic.
No,
It's okay.
no. You can write numbers. The problem is with reversible predicates. You have some problems, but there are no problems to use numbers. Okay.
Okay.
Okay. So nice. That's perfect. First line is perfect. Second line. What happened if it's not equal?
It's not equal. Yes.
Yeah, it's not equal to empty list. Perfect. Let's go to count numbers of my little dog. You can hear my little dog?
Yes.
Yes. Oh, sorry. Okay. List of trees. This is okay. If we have the number of the list of trees, we have to add 1. So, but that's perfect for piano. But let's go to use numbers. So, R2 is R plus 1. Okay.
Okay.
Perfect. The solution is perfect, but only the change is for change the numbers instead of piano. Okay. Okay. Let's go to the second part. Second part of predicate. Let's go to count in a list of 3. Count. Let's go to count in an empty list. What is the solution for an
0?
0. Perfect. And now let's go to count in a head tail. As we do always. And what is the head? The head. What do we have in the head?
A new tree.
We have a tree. Let's go to count the number of elements in the head. I don't know how many elements. What I have to do here? So when that is true, so sorry. What we have to do here with the head? With this tree, we have to count the number of elements, no? Or we have to count the tail and add 1. What do you think? We have to count the number of elements in the tail. If we have the number of elements of the tail is a list of trees, what is the total result? what is the total result for the full list? Can you hear me?
Yes, it plus the number of the head, but we don't know how many elements.
Yeah, we have. We have exactly. We have to count the number of
Yes.
of the elements in head. That is a tree. We'll have one element, or we'll have 1 million. I don't know. R and R2. And what is the solution?
It's R plus R2.
Perfect. Perfect. Nice. So the solution is R3.
You need to put the is, no? R3.
Yeah, exactly. Yeah. Perfect. Nice. Okay.
Just
Yeah, that's all. We have a predicate for list of trees and a predicate for trees. Okay? Okay, let's go to check if that works. Here, make. We have a singleton variable in 95. Let's go to resolve that. 95. Yeah, because we're not doing nothing with that. So let's go to put anonymous variable here, because we are not using this variable. So to make, now we have no errors of this thing. Count number of elements in a tree. This is the okay. Let's go to use listing the tree 1. We have 1, 2, 3, 4, 5, 6, 7, 8 elements. Okay, let's go to count. Sorry, tree 1 in tree T, and count T and N, and the result have to be 8. It's okay, it's perfect. No more solutions, it's perfect. And in tree 2 we have only 4 nodes. Okay, any question about that?
no.
It's okay.
It's okay.
Okay, nice. So for the first day, I'm gonna give you some exercise to practice at home. Try to resolve a predicate to add all the values in a tree. We have a tree, and we have to obtain n or r. This is input and this is output. This says it is true. It is true if r unify with the result of adding all values in 3 levels. Okay, we have in this tree we have numbers. So all levels in tree are numbers. Okay, so this exercise for the next day. Try to resolve that by yourself. Create a predicate to add all the values in a generic tree. Okay, and remember 2 parts and predicate for trees and a predicate for list of trees. Okay.
Okay.
I'm gonna share that file for you. You want to continue with that? Okay. Okay, nice. So, you have any question about
Not now.
this
It's okay.
previous exercise? You are understanding how this this way to resolve. You can find other way to resolve this predicate for generic trees, but I prefer to separate in 2 parts. For me, it's more simple to resolve. You can find another type of resolution for these trees, for generic trees, but I always prefer to do that in separate parts. One for the tree and one for the list of trees. Okay, so here we can apply the general techniques for list, like separate head and tail, and make the result for the head and make the result for the tail, and obtain the total solution. Okay, and this is a more simple case only to call to the list of trees and create the relationship between the list of tree and the full tree. Okay, and it's very simple. In this case, it's only at 1. It's depending on the problem, but here we have some very, very simple modification you have to do with the result. Okay. Nice, perfect. If you have, we only, as I told you at the beginning of the classroom today, at this lesson, we only have to learn 2 more things, are graphs and a state problem, right? Something similar to games. Let's go to resolve some games, similar to chess or 8 queens. I don't know if you know this problem, 8 queens or something similar. We can resolve with Prolog using state problems. Okay. So nice. I hope I can upload to YouTube this video and the other this week, and you can check if you want to remember some ideas. I will try to upload today. Okay.
Yeah.
Okay, nice. See you next week. Have a nice weekend and the rest of the week. Okay.
Thank you.
You too.
Bye.
Bye bye.
Bye.